Good morning. Oh, please save the applause to after. I hope everyone's not too hungover or too full from all the food last night, which was fantastic. What I want to talk about this morning is MyStorm. Hands up, who knows what MyStorm is? Or have heard of MyStorm? Okay, so it's about 50-50. My name is Al. My colleague at the back there is Ken, and we've been doing this project together, along with help from a number of other people, including Jeremy, who's going to speak and take part of this presentation. He's using this MyStorm board to actually develop his AAP altruistic processor. So what I want to do is just take you on a little bit of a journey of where we've come from and what's going to be happening certainly in the near term and talk about some of the features of MyStorm, etc., and some of the reasons we've done it. Well, it all started because of a certain person here on the front row back in December 2015 when Clifford actually produced Project IceStorm. And when I saw this, I thought, wow, finally, here is, a proper open source, complete system, including bitstream, something that I'd been looking for many years. And to my surprise, it was actually really easy to use as well. I thought, oh my God, this is going to be really difficult to install. There's going to be complicated library requirements, etc. But it turned out to be a really easy thing to get up and running. So that's really what kicked it off, because at that point I thought, well, we now have the open source software. We have a tool chain that people can contribute to and develop to move things forward. We now don't have to have the kind of large bloat that's required. Even if you want to do something fairly trivial, having to install gigabytes of different software is a bit of a pain. It's actually an entry to barrier entry for many people. With IceStorm, you can actually get stuff on very, very quickly. It's a very small install, and as time goes by, we'll find that it will be included in package managers, etc., and it will just be literally a few commands away. So this is really what incentivized me to get involved. I was delivering an FPGA talk at the Open Source Hardware User Group, which is based out of BCS in London. We meet once a month, not every month. We have a break in the summer. And this particular event had several different talks, including my own, where I introduced people to the MyStorm project and the possibilities of open source hardware, FPGAs, not so much chip development, but actually just getting into using FPGAs in an open source tool chain. Ken and I and a few others met in the pub afterwards, and it was at this point we decided we really should put together some good open source hardware that was based around the IceStorm package. In other words, to provide the open source hardware part to the open source software. One of the things that we wanted to do was build a AAA FPGA platform. The AAA in this case is affordable and accessible. What we'd seen mostly in the marketplace were rather expensive development boards, kits, etc. There seemed to be quite a bit of a premium on FPGA development and getting into that market. One of the purposes of getting the pricing down to our target retail price of $30 is so that people don't have to think about it. What we see now, certainly on the microcontroller front, is people not worrying too much about buying these boards. They don't just buy one, they buy several in many cases, and they put them into things for their prototypes, etc. So there's a ready market out there for people, from software developers that looking at getting into hardware, existing hardware developers that maybe haven't touched FPGAs before, always wanted to, but haven't had a good opportunity to do so. There is also FPGA developers themselves that might want to play with something that is slightly different. By hitting this kind of $30 price point, it's the amount of money that really people don't worry about spending, which was why it was our target. And you will find a lot of boards priced in this area for microcontrollers, and even lower now from Chinese manufacturers. So that was quite an important point. The other thing that we wanted to do was integrate the FPGA and the ARM tool sets. There's already a lot of microcontroller code out there. People are very familiar with developing microcontrollers, and we wanted to give them, you know, that facility alongside the FPGAs. So you can really think of this development system as having a hard core. I'm not going to suggest that we have an AXI bus or a wishbone between that particular core and the FPGA, but we do have mechanisms for moving the information and making the communication between those devices more fluent. And of course, it had to be open source hardware and open source software. So wherever possible, we're using as much as we can out there. We're trying to stand on the shoulders of giants. If there's code already out there that we can use, we want to use it. If there's hardware designs out there that are proven, then we want to use and leverage those. The other challenge we set ourselves was that we were going to do this in 3 months. OSHUG community has an annual event in Hebden Bridge, which is in the north of England, in Yorkshire. And that was occurring at the beginning of September. And Ken and I, being the people we are, said, oh yes, we'll do an FPGA workshop, you know, at OshCamp, and we'll have our product working in time for this. Foolishly, we decided to do this. So we actually set ourselves a target to do this in very short order, to go from virtually nothing in terms of hardware design to a hardware product where we'd have to have enough units for people to actually run the workshop on, as well as having some sort of tutorial for them to go over. It's always quite useful to have this kind of constraint and this kind of pressure, otherwise you spend a lot of time designing something and you go round and round and round, not making decisions, etc. So when you know you've got to deliver something to a bunch of people that are turning up to an event, you get onto the job pretty quickly. So we had June and July. We spent quite a bit of time finalizing the schematic, deciding what we were going to include, what we weren't going to include. And in fact, the hardest bit was deciding what we weren't going to include. Having had the $30 constraint, that doesn't actually leave you much room in components. We certainly went through this process of, shall we have a lot of things on the board in terms of things that people can play with? Should we have a 7-segment display on there, for example? They're not very expensive. We could put it on the board. But eventually, we came to the conclusion that what we would have on the board in terms of things that would actually do anything, we would want to minimize that, because what we actually wanted to do was maximize the connectivity on the board. So in terms of what you would find on the board, there wouldn't actually be a lot already on there that you could play with, but enough to get your basic FPGA and ARM program running and showing something, in this case LEDs. We then spent quite a bit of time laying out and trying to get it in a form factor that would be low cost. The other thing that we're doing with this is we weren't using the BGA parts because we wanted to confine ourselves to using a relatively low-cost PCB manufacturer that we could turn around quickly. So it was basically a 2-layer board. Probably with just the FPGA, that wouldn't have been a huge problem, but when you combine that with the ARM chip and you want to get to the ARM I/O as well as the FPGA I/O, it became a bit of a challenge in terms of layouts. But we did get to a layout that we were happy with, a slight compromise. We got some, we sourced the chips ourselves. We were worried about getting the quantities that we wanted. The lattice chips, for example, are not necessarily as well known in the Chinese marketplace where we were going to get these things manufactured. So we decided to get the silicon ourselves. That was a bit of a problem. It's really not a good idea to do this. If you're going to do your sourcing, get it all sourced in China, or at least delivered in China, because getting stuff into China now, even via the couriers through Hong Kong, is very difficult. You'll end up paying a premium on top of your components. You'll slow yourself down. So we had some interesting problems actually getting the chips to Toby. And Toby is our representative in Shenzhen. He's the guy that actually gets these things assembled. So by the 30th of July, Toby had 50 of these units made up and assembled. But prior to that, what we did first was we took 3 of the boards that we have designed and we actually populated them by hand in my kitchen using a small aluminium reflow block that I built myself a number of years ago. That was a lot of fun with 0402 components. It took quite a bit of trial and error, but we actually got 3 units up and running, and we had Blinky running at least on the ARM at this point in time. And that was telling us that our basic hardware circuitry was working, which was good, because we were just about to press the button with the Chinese manufacturer in order to get it out by the end of August. So we had our first Blinky running on the ARM Cortex in July. So, of course, we thought, beer o'clock, celebration. We have Blinky working, so we went down to one of our local watering holes and had a few beers and discussed what we were going to do next. And then started panicking about the fact that we had to get these things by September in 15 minutes. Next thing we had to do was work on getting the bill of materials. When you're having something made remotely, you have to have very clear instructions. And Ken spent an awful lot of time. Okay. And Ken spent an awful lot of time getting that so that it was clear, which is quite difficult on a rather dense board. As I said, we sourced the main silicon ourselves, which we managed to get over to Toby just in time for the production. And Toby actually sourced all the local passives himself, buying them on reels for the pick-and-place machines. In fact, the passive that he's got will probably keep us going for a year, I should imagine. He then put it through the pick-and-place SMT, using the contract manufacturing services, or a number of companies that he works with over there. They do some final finishing by hand in some case. One of the things that we found out from this production run is we had some tombstoning problems with our 0402 decoupling caps and some of the resistors as well. Some of the things that we've got to fix here, these are just thermal problems that you have on initial runs of boards. And then the boards were delivered, hurrah, to Hebden Bridge right at the end of August, about 5 days or 4 days before we were due to present that weekend. We hadn't seen them at this point. We knew they were in Hebden Bridge, and we were getting ready to go up there for this. One of the things that we did have to finish ourselves is soldering on the actual headers. So the non-surface mount stuff that couldn't go through the pick-and-place machine had to be manually soldered. That was partly because we didn't get those in time. They were sourced quite late, but again, sourced from China. And we did have some issues because not everything we wanted we could get at the time due to a minor documentation cock-up in our build instructions, bill of materials. The other thing that I had to do personally, along with another colleague of ours, Mark, is actually get the tools running on this configuration because it's slightly different. The boards that we'd seen that are out there from Lattice, etc., are based around an FTDI chip that reprograms the SPI RAM that the Lattice will boot from or get its boot image from. We didn't want to go that route because we thought the FTDI products were rather expensive for what they are, and we wanted to use the ARM chip to do this. Of course, in doing so, you set yourself the problem of, oh, well, now we have to work out a way of getting the ARM chip to get the information to the FPGA, the lattice FPGA. So we basically chose a larger ARM chip that has a lot more flash, that is capable of actually holding the bit file, the bitstream file, and we actually inject that into the lattice ICE product in a slave mode over SPI. But all of that software had to be run. We were also worried because we didn't know what equipment that the people attending the workshop would have. And we were worried about, holy crap, how are we going to get this working on Windows? You know, at this point, we'd only worked with the Linux tools, etc. So we decided what we would do is we will actually use Raspberry Pis. Because Yosis, being the way it is, small, etc., it's actually very easy to get it installed on a Raspberry Pi. So you have the entire tool chain, including the ARM cross-compiler, and we have a little Raspbian image with all the bits and pieces we need. Therefore, we can just give everyone a Raspberry Pi. We didn't have the Raspberry Pis, but some of our colleagues at Pimori had them, and they lent us enough Raspberry Pis for it. So we had the entire tool set on a Raspberry Pi, and then all the user does is they literally SSH or log into their Raspberry Pi. Some of them actually turned up with their own Raspberry Pis and screens on and programmed it from their Raspberry Pis. Some others, more experienced, used their laptops through to the Raspberry Pis and actually compiled locally because they had the tools on, etc. But we had a solution that meant that we didn't have to worry about the Windows problem. However, we did have to bring all of that together and build this Raspbian Pi image. And that really came together. Both Ken and I were presenting on a Saturday doing our talks. The workshops were on a Sunday. I finished writing the code about 9 o'clock on the Saturday evening. So left it slightly late, but we were ready to go in the morning. So, as I said, it's Ken up there on the left doing his talk about education and open source approach to education. I talked about Yosis and IceStorm and FPGA development in the open source hardware and software. And there at the bottom, you can see we had a full house. We were totally oversubscribed. We had, I believe, 20 spaces. We had about 30 plus, 33, 35 different people that wanted to go onto the workshop. It was a bit of a problem because we didn't have that many cards. We'd only budgeted for 25 attendees. But we just got people to share, etc. We were also going to give them a card to take away as part of the workshop as well. And we still owe a few people cards on that front. We do have some of those. We just haven't distributed them all to those members. And the workshop went very well. So I did a basic FPGA Verilog tutorial and got people up and running. They ran their first Verilog programs on a piece of hardware. And everyone was, suitably impressed. At that point, we kind of went, whew, thank goodness. And we kind of relaxed for a bit and thought, wow, that was good. Let's sleep for a week and then move on to what we were going to do next. And Hebden Bridge is a beautiful place as well, by the way. It's right by the canal. And it was actually very good. Seasonally, Yorkshire tends to have a lot of rain. It's probably not the brightest place in the world, but on this particular occasion, we had some fantastic weather for the event as well. So it was absolutely lovely. So this is September. Now we move on to October, where we are now, here at ORCONF 2016. And thank you for inviting us to speak. We're launching the MyStorm SDK. So this is a variation on the board that we had at the workshops. One of the things that we changed on this compared to the workshop board was that the workshop board was an STM32F103. It has capacity for 1 bit file image and some spare memory left over, flash, for you to put your program in, etc. That is an M3 device as well. So we thought we wanted to do something a bit more special for the software developers and hardware developers out there that we wanted to get these boards out to first. So we went a little bit over the top and chose basically one of the best ones that we could get, which was an STM32L476. Now the 476 is an M4 rather than an M3, so you have floating point unit built in. That makes it easier for some people because they don't have to worry about the latency of floating point, software versions. You can actually do it in hardware. That gives them some flexibility. Not only that, but it has a larger amount of both RAM and flash, and you can put several bit file images for the FPGA in there. The lattice ICE40 that we're using is the HX4K. Now, even though that has 3,530 lookup tables, that we believe is constrained by the lattice tools. Actually, the hardware is an 8K die, we understand, and we don't believe that that's disabled or limited in any way. So if you're using the IceStorm tools, you will find you actually have access to about 8Ks, 7,500 lookup tables rather than the 3,500. Worth remembering. That's a nice little bonus. We're probably not going to shout about that because we don't really want to upset lattice at this point. On board, we added a 256K 16-bit SRAM, and that actually sits on the rear of the board. I have a board here, actually. You can see the size we're talking about. I've actually got an ST-Link 2 programmer hanging off it for the ARM32 because I prefer to use that for my development processes. So as you can see, this board is actually a 75 by 75 millimeters. It is predominantly I/O connectors around the outside. Those are your FPGA connectors based around PMOD pinouts so that you can add existing PMODs if you use those. We're working on a whole bunch of those as well. We want to put some low-cost PMODs out there to go with this. Inside, from an I/O point of view, we have a number of other features. We have an Arduino pinout that is connected to the STM32. So folks coming from that kind of environment can take advantage of that if they have shields, etc. And this microcontroller has 5-volt tolerant IOs as well, which is really handy in that sense. So in total, we have 13 PMODs, some of which are single PMODs, some of which are double PMODs. So there's plenty of I/O. We've got 52 SysIO lines coming out from the FPGA. Additionally, this header on this side here is a Raspberry Pi compatible header. Now, the reason we did that is because initially we were using the Raspberry Pis as a means of programming. And we figured it would be good to make the Raspberry Pi connection as well. That enables you to program the entire thing from the Raspberry Pi. And the way that it does that is it uses the UART bootloader in the 476 or the STM32103 to actually transfer the bit file. This 476 also has a DFU bootloader installed by default, and we intend using that as a means of getting the binaries up and down to the device. We haven't finished the work on that at the moment, which is why I'm still using the ST-Link. As of yesterday, I managed to get some basic MPEG support for the 476. We had the code that we wrote for the 103, we couldn't get that working with the 476. That was using the STM libraries. And we were kind of worried because we were thinking of using the GDF36, the Chinese variants, to lower the cost. And in order to do that, we needed something that wasn't an ST licensed piece of software because they get very upset if you're using their software with someone else's chip, unsurprisingly. So one of the things we looked at that had the widest support for the different STM32 parts of this equation was Mbed. And they tend to have their hardware extraction layer support out very, very early on, before anyone else. And if you look at the ST development Nucleo boards and the Discovery boards, they cover all of their bases very quickly on this front. And yesterday I got that working with the 476, which is good, bit of a relief for me, because that was a bit of a nightmare on the SDK side. What are we going to actually ship in quantity? Well, in November, probably towards the ends of November, we're actually working on this right now. We're going to ship MyStorm Black Ice, which will be, if you like, the bulk shipping, the consumer-facing version of this product. There's a few changes on there. Again, you see the same ICE 40 HX4K chip. There's no changes there. On board, again, we have the 256K of 16-bit SRAM. What we have changed is we are using the STM32L4 free ARM Cortex M4. So initially we were looking at using the Chinese GDF32, which gives us very good memory in terms of flash size, but it's not as high performance, and we also have some issues doing the drivers for it. Going this route, we get a very reasonably priced ARM that has a number of benefits, including the fact that it's got the M4, so it has a floating point CoPro in there. But it also has lots of flash, 256K, as well as 64K of RAM. It also has some other nice features, like a 5 megasample ADC. You know, one of the reasons we wanted to use the STM on there is to add in an ADC part to that equation. And that allows us to do that. Not only that, it has two DACs built in, which is very useful. And it also has some analog comparators as well. So it's got some fairly handy analog components that can be integrated with the FPGA indirectly. It's also got a talk about a fast umbilical FPGA and ARM interface here. And I'm experimenting with different ways of getting that ARM Cortex to actually communicate with the FPGA device and try and make that as seamless as possible for anyone on the STM32 size. And we've got several ideas there. And I'll probably talk about those a bit later if someone wants to come and talk to me afterwards. We've actually slightly increased the number of PMODs by juggling things around a bit. So there are a few more IOs over the SDK board. 60 sysIO lines. The Arduino Shield headers are the same, of which we've got 4 extra shared IOs on there between the FPGA and the STM32. That just enables us to get the FPGA talking to a Shield on those extra pins for those that want to use that. The Raspberry Pi header has been replaced with a general header. This is really a communications header. On there we have SPI, I2C, UART, as well as the ST-Link pins, all of which are following the original Raspberry Pi pinout on a 26-pin header. So they are backward compatible with the older Raspberry Pis as well as the new Raspberry Pis. And at the same time, it's not taking up quite as much room on the board and gives us a bit more flexibility in terms of how we lay things out. We also had quite a lot of let's say, non-Raspberry Pi supporting Americans telling us that we shouldn't be completely Raspberry Pi centric, and we figured we should cater for that market as well. There were a lot of Raspberry Pi lookalikes, headers. There are a lot of other embedded type platforms that have, you know, simple Linux, etc. on that we want to get this working with. We don't want that to be a barrier to people. Again, we have the USB interface supporting DFU programming. We have added, or I'm actually in the process of getting this operational at the moment, we've added a micro SD card socket. This is accessible from both the ARM and the FPGA. This is useful for storing multiple images, for example. It's also really useful for things like data logging, large amounts of data onto storage, etc. when it's used as a standalone platform in some sort of device. So we figured it would be nice to have this feature in, so we've added this. And we still believe we can hit our $30 cost with all of these modifications. I will ask towards the end whether there's any feedback from you guys on things that you think maybe we should be doing as well. I just have the note there that actually that ICE 40 is effectively their 8K device in terms of the die inside there, as I mentioned earlier. So what is MyStorm for? Who's going to be using MyStorm? Who did we imagine would be interested in taking something like a MyStorm? It's first and foremost, it's an entry-level FPGA development platform and board. It's an easy entry. That's the entire idea behind this. We want it to be accessible in terms of cost, and eventually accessible in terms of easy-to-use software, although that's going to take a lot more time to get spot on. So it's going to be ideal for the educational market and also for the hobby market, etc. This is really about lowering the entry barrier to a whole range of people that previously wouldn't have had access to this market. And that is one of the very key things and one of the important drivers for Ken and I. You can also use it for designing simple systems on a chip or app glue logic. Now, when I say simple SoC, Clifford's done a very good example of this with the ICO board software. I show you what you can actually fit into, 4 or 8K with the Pico 532. How many gates is it, Clifford? About 1,300 or something, just for that before you start adding the peripherals. Yeah, it's a relatively small number. It's surprising what you can fit into this number of gates. Classic cores seems to be very popular. Here you're talking about things like Atari games, etc., old console games. People love getting FPGAs to behave like these old game consoles and stuff. There's a very big market for this. People spend an enormous amount of time in recreating these games, either because of their own experiences in the past that they want to recreate, or because it's a really good challenge for them to learn about, using FPGAs and designing processors, etc. There are people designing, recreating the Apollo computers, for example, on FPGAs. And we're going to see more of that. Yes? Yeah. And just for generally learning, so you could be using it to actually create your own very simple processor, or just something as simple as an ALU unit. Ken has a favorite book. What's it called, Ken, that learning book? The course? Yeah. And do catch that, because that's really interesting from an educational point of view. Some of you, like Ken and I, who may have been around a little bit longer, have kind of learnt this stuff from very, very basics. Originally we were building logic circuits and doing things like that. So we have the luxury of having been through all of these pieces, but many of the modern students don't get that luxury. They're kind of fast-pathed past all of this, and that literature and those ideas is a very powerful way of getting that across in a short amount of time. And we think that will work very well with MyStorm. Experimental cores. So here we're seeing something slightly different. These are, you wouldn't have seen much of this before, but you're now starting to see a lot of it where people just think, oh, I will try this because this interests me. So for example, the fourth core. There's a lot of people that just love fourth and that work. So implementing a core, in 150 lines of Verilog that runs fourth is, just really cool, in my opinion. I mean, fourth isn't my favorite language. Reverse Polish isn't a natural way for me to operate. But doing something that small in that few lines of Verilog is just, stunning. Minimum instruction set computers. You know, how few instructions can I create a computer in? There's lots of people doing this kind of thing as well, which is very interesting. And then there's the altruistic processor, which Jeremy's going to talk about a little bit later. And that is really designed to actually find holes in compilers and exercise parts of compilers that aren't normally exercised by the existing hardware choices that are out there. Embedded cores and RISC-V, we've heard a lot about this this weekend. This thing's going to take the world, I'm sure. ARM probably aren't shaking in their boots, but they really should be. I think what we're going to see in the future is a RISC-V world, whether people like it or not. It's moving so quickly. You can do some very basic stuff, fitting it into this small amount of memory. Don't expect to be able to do a fully blown RISC-V implementation, but certainly something like the Pico RV32, as Clifford has shown. Zip CPU, which was really interesting yesterday. You can certainly fit that in this very easy. Something that I do, I work in robotics generally. That's how I get my mortgage paid. And motion, so field-oriented control of brushless DC motors, etc. And direct drive of DC motors, where you see, you know, these cheetahs and the Ghost Minotaur things, that kind of walking on legs using brushless control motors without gearing, etc. There's quite a few of us working in those areas. That's very difficult to do on a microcontroller, but when you combine microcontrollers and FPGAs, you can go a lot further on that sort of thing. And I think that's going to become a lot more prevalent. Obviously, digital signal processing, although the Lattice don't have any DSP parts within their cores themselves, you can build multipliers, etc., adders, etc. Audio is another area we've had a lot of interest in. There's a number of people out there that want to do audio products of different sorts using the MyStorm and Lattice type products. Image processing, certainly at a low level. Your limitations here really are your amount of RAM more than anything. But again, you could do basically flow processing, low resolution flow processing for drones, that kind of thing, or small robots. Hybrid computation, this is an interesting one. We've seen quite a few talks that talk about accelerating AI, and I'm not talking about accelerating the training here. The training would take place in a normal mechanism using, you know, GPU graphics cards or online parallel concurrent cloud services. But in terms of the small inference machines, you can actually build some fairly small sensor-based neural network sort of stuff on these as well. And I'm very interested in very small neural Turing machines, which is a generic way of doing things like long-term, short-term memory processors and recurrent neural networks on very small scales. And I think we're going to see a lot more of that kind of work done on FPGAs more generally, both at the low end and the high end. Let me briefly talk about software and tools. One of the issues that we have, quickly on this is obviously it's IceStorm based, and in order to get MyStorm working, you need an ARM compiler set, and you also need the FPGA, Yosis, and Arachne, etc. We found something called Platform IO, which is now supporting both of these setups. So once you install Platform IO, you can then pull down the necessary things for your projects. That makes it easier to get things installed without having to manually install for those that are not used to having ARM compilers and FPGA tool sets and tool chains. So we're doing some work on that to make it easier. The future of MyStorm, there's some quotes here that we've seen. Yosis is GCC for hardware. We're seeing, you know, von Neumann kind of running out of power at the top end, and FPGAs being used to accelerate things. But what we're most interested in really is this new complete open source palette on which we can build new tools. And let's challenge some of those basic assumptions. And now I'd like to hand over to my colleague, Jeremy, to talk about the AAP. And I'll be around for questions afterwards as well. Any questions while Jeremy loads this up?
You know, having spent a whole lecture yesterday talking on how every LUT is precious, that's a small number of 4 LUTs, and I'm real used to 6 LUTs. One of the real uses that I would see for a small board like this, you already brought it out, is robotics and robotics controllers. A robotics controller really needs to be a tight real-time system. You can build that with your own CPU, such as the ZIP CPU, nicely inside of an FPGA. Why not just dump the ARM processor and beef up the FPGA? That gives you more capability for a real-time system, more capability to work on your motor, reading from your encoders, knowing where the motors are at, getting that real-time system working, reading and writing from your SD card, all of these other pieces. You get enough place for both your peripherals and to tightly couple the peripherals with the FPGA.
My answer to that would be fairly simple. This is the first shot and the easiest way of getting there. Going on to that next stage with the larger, it will put the cost up considerably because the FPGA alone will cost $25 minimum.
Yeah, but if you drop the ARM?
You've still got $25 for the FPGA. Okay. So you're already in a different price bracket. But it is something we're considering. Really, the way to look at this is that hardcore takes the necessary need, you know, having to have the soft core in there. That doesn't mean that you don't want to run the soft core. Many people will run the soft core and not even use the hardcore. And we will look at doing larger ones later.
All right.
Okay, thank you, Al. So this was going to be a lightning talk separately, but it follows on from Al. It's just a quick update on AAP, which we presented last year. AAP is not really intended to be put into products as some fancy new processor. It is the compiler writer's architecture from hell. It's designed to advance the state of compiler technology. So everything that causes compiler writers to have sleepless nights is combined in one architecture. To make it real, it needs to be on real hardware. And one of the pushbacks from the LLVM community about accepting this is this some esoteric thing that no one's interested in? So we're trying to make the point, it's got real hardware. Dan Gorringe presented his implementation on DE0 Nano at CERN last year, and you may be interested to know that for that work he also won the British Computer Society Student Prize. So we've got AAP being used, but it's going to be also used as a processor on MyStorm because it's so much easier to use the OSIS tools. Quick update. So that's the architecture, Harvard architecture, multiple code and data memories. The code memory, one thing we've changed this year, the code memory can be 16 or 24 bits wide, so we can experiment with non-power of 2 units of memory. The data memories can be byte or word, so we can explore issues like what happens when characters aren't 8 bits long, which is immensely painful. The ISA is stable. It hasn't changed much over the last year. As I say, those two things. And we've got AAP pushed up to the LLVM community. Anyone who's involved in LLVM, we'd appreciate you saying, why is the AAP stuff not yet up there? There is an element of, you know, persuading the AAP community, the LLVM community, this stuff really matters. I have spent the last few weeks trying to get this all up and running on MyStorm. It will be supported as tutorial. It's intended to be a reference for a future chip hack weekend, which is a course we run occasionally to take hobbyists into FPGA programming. So it's in progress. It's 16-bit instructions only. It's only got 16 registers at the moment because I can't fit them all on. The status is it compiles and executes on Verilator. And the compiler generated this program for me, which adds 1 to R0 and sits in a loop. It synthesizes for MyStorm, no problem, using Yosis, and it'll easily fit on MyStorm. But it doesn't run. And the reason is, Al pointed out to me the glaring omission. I've got one of the very early MyStorm boards, and where the memory chip should be on the back is a little sign saying IC1 and no memory chip. So we'll remedy that later today. But just to prove it, there's Yosis running and giving me some nice output. There is the AAP starting up. We use the UART for debug, just for easy tutorial migration. We teach you how to implement a UART, then you can use it. And we have a little simple character-based protocol for controlling the processor. And there, if you can see at the bottom I'm showing R0, and you can see it's going 1, 2, 3, 4. It is actually counting up, and my program's executing correctly. So thank you very much. And while the next person changes over, any questions?